Okay, so in this next video we're going to see why the complex numbers forms a separable metric space. Okay, the metric space we're considering is the complex numbers with the usual Euclidean metric on the complex numbers, i.e. The distance between two complex numbers, which we'll call z and let's say w, is given by the absolute value, or the modulus, the complex modulus function of z minus w. So if we have a picture, here's the complex plane. And if you have two complex numbers, let's say this is z and this is w, then you can take the complex number z minus w, which as a vector corresponds to this vector here, z minus w. So the way of seeing that is that this is the vector z here, and basically you're taking minus w, which is that vector, so overall they add together to give that vector. And basically when you take the modulus of that complex number, z minus w, you're going to get the length of that line. Okay, in the normal Euclidean sense of the length between 2 points, i.e. if you measure it with a ruler. So that's the metric we're going to define. We know that this forms a metric. We've seen that many times before. What we now want to understand is why this metric space is separable. And remember, the definition for separable states that what we need to find, what we need to show, is that there exists a countable subset of this metric space. And note that the complex numbers is not a countable set. The complex numbers is the real numbers crossed with the real numbers, effectively. It basically, you can view the complex numbers as being the real numbers Cartesian producted with the real numbers, and the real numbers are not countable. Therefore, the complex numbers certainly are not countable. Indeed, the real numbers are a subset of the complex numbers. So if the real numbers are not countable, then the complex numbers are certainly not countable. So this is not a countable set on which we have a metric defined. So we can't just use that initial property, that initial, if a metric space was countable, then it's certainly separable. So instead we have to find a proper subset of the complex numbers, which is countable and which is dense within the complex numbers. And the subset you can find is called the Gaussian numbers, and it's given the symbol q with brackets, curly brackets, I in there. And that is all things of the form alpha plus beta times I, the imaginary constant, where alpha and beta are both rational numbers. So basically, it's all complex numbers where the coefficients of the real, all complex numbers where the real and imaginary parts are rational numbers. So a complex number like the square root of 2 plus 3i is not an element of the Gaussian numbers, whereas things like 3 over 2 plus 5 over 2i is an element of the Gaussian numbers. So it's all complex numbers where the real and complex portions, alpha and beta, are rational numbers rather than a general real number, because of course the complex numbers is this, where alpha and beta are real numbers. Okay, so what I now want to prove is that if you first thing we need to prove is that this is a countable subset. So the way that you can show this is that it is the Gaussian numbers, this set, is effectively, we can put it in bijection with, let's make a mapping f, which is going to map it onto the Cartesian product of q with itself. So let me show you what I mean by that. So we know that the rational numbers is countable. We proved that in the last video when we were proving that the real numbers is a separable metric space. So basically what I can now do is list every single rational number along here. So rational number 1, which I'll just call q1 here, q2, q3, q4, q5, etc. You can list them all out because they were countable. Similarly, you can list them out again down here, q1, q2, q3, q4, q5. Then what we can do is we can create the either you can think of it as creating the ordered pair, or you can think of it as creating q1 plus q1i. Then we can have q1 plus q2i, which is the one corresponding here. So put all of these in front of the I, and put all of these in front of the real as the real portion. So q1 plus q3i, etc. You go on, and then you'd have q2 plus q1i. So you'd have this one now as your real component, and then you'd have q2 plus q2i, and you'd have q2 plus q3i, etc. And going on to this final line, we'd have q3 plus q1i, q3 plus q2i, and q3 plus q3i. So you could do this, and you build up this great big long table. And the reason I said, you know, it was in bijection with this Cartesian product is that you could also think of these as being Q1, i.e. you could think of this as being the ordered pair Q1, Q1. Instead of writing all out the ordered pair, all the ordered pairs, instead I've written out exactly what they'd be in this, if we were just imagining this as a great big lattice like this. So basically we can write out the Gaussian numbers like this in this great big lattice form, and that's very interesting because now what we can do is apply Cantor diagonalization. We can say, okay, we want to now put this entire set in bijection with the natural numbers. I've missed out a step in this proof actually. What I should show you is that every single element of the Gaussian numbers is going to be somewhere within this table, and the reason is that every possible rational is going to be up here and every possible rational is going to be down here. So somewhere, you give me any two rational numbers you like. So let alpha be some specific rational number and let beta be some specific rational number. There will be alpha will be in this list, so I can find alpha down here somewhere, and beta will be in this list, so I can find beta. So in principle, I could work out where you are in this table. Okay. Now we just apply Cantor diagonalization. So we know the natural numbers are here: 1, 2, 3, 4, 5, 6, 7, 8, and basically what we're going to do is match this one here, and in fact I'll do this in colours, match this one here to number 1, so this is going to go to number 1, so here's number 1. Then we can go along up here, and we'll match this one up to 2. We'll then go down to here, and we'll match that one up to 3. I haven't got any more colours. We've got this yellow. We'll go down to here and match this one up to 4, and then we'll begin over again with the colours. Right, I mean, we'll go Q2 plus Q2i. We'll go to 5. We'll then go to this one up here, Q1 plus Q3i, which will go into 6, and then I run out because I would have to go here next, and then here, 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 etc. You go along in these diagonal chains like this, and you basically will go through every element of this table. And since every element of the Gaussian numbers is somewhere in this great big lattice table thing, every Gaussian number will be in bijection with some natural, well, will be mapped onto some natural number. So in principle, I could tell you, you give me any Gaussian number, I can work out which of these, sorry, I can work out which natural number it's mapped onto. And the nice thing about this is, unlike in the proof that the rational numbers were countable, you're not going to get degeneracies. You're not going to get two of these being the same thing. All of the elements of this table are different because this includes all the rationals, but it only includes each rational once. This includes all the rationals, and it only includes the rationals once. And each combination of them is a different Gaussian number. So you're only going to get, you're not going to have to skip bits out like you did in the great big chain for the rational numbers. Okay, so that's the proof that the Gaussian numbers are countable because the rational numbers are countable. So now what we want to prove is that we want to prove that if I take any old complex number, let's say x, in fact let's call it z, which is a complex number, so z is just any old complex number, I want to prove to you that this set is dense within here, which means that if I take any complex number and I take any epsilon greater than 0 and construct, sorry I keep missing the dashed lines, this is an open ball, construct an open ball around z, or you could call, because it's the complex plane, it's often called an open disk. Construct an open disk around z of size epsilon. I want to prove that there will be a Gaussian number within there. So I want to prove that whatever epsilon ball you give me around any arbitrary complex number z, that there will be an element of this set within it. So the way that you do that is, firstly, let's draw a bigger picture. Let's take z here and draw a bigger picture. Well, z firstly has two components, so let's write that out. Z is equal to some x plus some iy, okay? and we are now taking the open disk, or the open ball, centered at Z, of size epsilon. So basically, the way we're going to prove this is just by doing the proof that the real numbers were, that the rationals were dense in the real numbers. We're basically just going to do that twice. So what we do is we consider putting like a horizontal line through here, and just consider points on this horizontal line. So we fix the imaginary part and just vary the x part, basically. Okay.